Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Mehdi Tajvidi, who is an associate professor of renewable nanomaterials in the School of Forest Resources at the University of Maine. I've been a fan of Mehdi's research area for years and was really happy that I was able to learn more about his work and his research at the 2024 Maine Science Festival, where I moderated a panel he was on that was centered on forest products. Mehdi is doing really great research on applications of nanocellulose. Our conversation was recorded in May 2024, and I hope you enjoy it as much as I did. Today's episode is supported by Maine Technology Institute. MTI is celebrating 25 years of making grants, loans, and equity investments to businesses, organizations, and entrepreneurs to strengthen Maine's innovation economy. So, Mehdi, welcome to the Maine Science Podcast. I have been a fan from afar of your work for a little bit. I will expand on that once we get to what your current research is. But before we do that, I was hoping you could let me know how you got into forestry research and forestry science and eventually made your way to Maine.
Well, yeah, that's an interesting story. When I was a kid, I wanted to be a doctor. I was secretly hoping I would become a magician at the same time. So you put these two together, I guess I am a doctor, but in a different sense, I would say. I have a PhD, so I call a doctor, but not a medical doctor, which I was actually imagining when I was a kid. Again, I applied to the to the medical school. I was short of 6 people to get in. So I didn't get in, and then I wanted to do something in engineering field. So I got into the University of Tehran in Iran, where I'm originally from, and I majored in what we called wood and paper science and technology at that time. And I did all my education there, basically my bachelor's, and then continued into my master's and PhD in the same university. And then during that time, I had an opportunity to come to the US. When I was a PhD student, I went to Madison, Wisconsin, to the Forest Products Laboratory, which at that time I didn't know how important it was to have some time there until I actually interviewed for a position here at Maine. And then people said, "Oh, it seems that you've been at the Forest Products Lab before." And I said, "Yeah, is that important?" And they said, "Yeah, it's very important." So I was here for about a year, and then I did most of my experimental work for my thesis here in the US. And then I got back to Iran. I defended my dissertation and became a faculty right after that at the same university. So I never left the same university. I was there from early on. And then I was there for a total of about 8 years as a faculty in the Department of Wood and Paper Science and Technology. And then I had a position offer from the University of Tokyo to do research for 2 years, funded by the Japanese government on the recyclability of composite materials made out of wood and natural fibers and plastics, which was in line with my thesis for my PhD. And then I basically went to Japan. I got back after 2 years and a half. Then I stayed another 2 years, and then I left for Canada, where I was a visiting professor at the University of Waterloo in chemical engineering. And then I got this position at UMaine that opened up. I interviewed for it and got the position. So that happened in 2013. So I joke that I am actually older than I look, because putting things together, I could retire maybe in a few years, potentially.
You can't retire yet. You've got too many cool things you're working on.
Yeah, I've been here at Maine since September 2013. So I'm happy here and call it home.
Well, I'm certainly glad that you're here. I think natural resources engineering, which I believe is what your degree is in, is not an obvious match with a forestry school. I mean, it is if you think about it for a second, but at first glance, I don't often think of engineers being in forestry schools.
Yes, that's a distinction. Engineers are normally defined by people who take the statics, mechanics of materials, the strengths of materials, and design abstraction, those things. And those are the things that we actually took as an undergraduate program. So our undergraduate program was on the borderline of engineering and science, I would say. And then in many other places, these departments of wood and paper science and technologies are separate departments. Here at UMaine, we have a School of Forest Resources. So there are several other disciplines there. We have parks and tourism, for example, in the same school. So we are a school. We are larger than a department. That's why I am there. But I also have appointments with our Advanced Structures and Composite Center, which is the ASCC, or we call it Composite Center. and also the Forest Bioproducts Research Institute, which are basically more engineering related disciplines.
So has your research always been on wood and what you can do with the parts that make up wood? And then I'm going to stop and let you dive into what I think is actually just so cool what you're doing.
Yeah, for all my graduate program for master's and my PhD was on what we call wood plastic composites, or WPCs. You see those like Trex is a famous brand here in the US where we can buy like composite decking and railing for your decks. So that was the material I worked on for my graduate program. And during my previous academic positions in different places, I mostly worked in the same area, but I was, again, working on some other aspects of wood-related materials. And then I got into nanocellulose, like at the very end of my career back in Iran. My last PhD student had an interest there, and that was a hot topic at that time. So we delved into it a little bit. But then since I arrived here in Maine, I'm exclusively working on nanocellulose applications in different industries.
So this is a great time for you to explain what the heck nanocellulose is and what it can do and how it can be used.
Yeah, so in general terms, nano is a unit of measurement, basically. So give the listeners some perspective. Human hair is about 100 microns. And 100 microns is 100,000 nanometers. So if you are talking about a particle that is 1 nanometer, you can put 100,000 of them side by side, and it will be as thick of a human hair, right? So we're talking about that dimension. But that does not necessarily mean that all of the material that we are working with are in that range. By definition, a nanomaterial is something that has one dimension smaller than 100 nanometers. So it can be a long thing, but has one dimension smaller than that range. And the nanomaterial that we are talking about are cellulosic nanomaterials, or sometimes lignocellulosic nanomaterials, which basically come from wood. So everyone has seen paper and pulp, I would say, right? So if you take that one and then grind it and grind it and grind it so much that you get to the smaller parts that are already in wood. So we don't synthesize those. They are already present in wood. We just liberate them and just extract them. And when we get them out, they are at least in one dimension, they are in that range of nanoparticles. So we call that material a nanostructured cellulosic material. There are different names for them because they are made in different ways. But normally that's what we have. There are two major types of these nanomaterial. There are many types, but the two major ones, one is called the CNF, or cellulose nanofibrils, or cellulose nanofibers, that are mostly produced by a mechanical disintegration or grinding process. You basically put pulp in water and grind it until it is very small. And the other materials are what we call cellulose nanocrystals, or CNCs. Those are mostly produced by a chemical process like acid hydrolysis, that you can use to wash all the areas that are not strong enough in the pulp fiber, and then you end up with small particles in nanoscale. So those are two very different types of these nanocellulose, but collectively they are called cellulose nanomaterials or nanocellulose in general. So when I started here in 2013, a year prior to that, 2012, there was some funding at the federal level to establish production lines on pilot scale to produce nanocellulose materials. And this was split into half. Half of that was invested at UMaine, and the other half at the Forest Products Laboratory in Madison, Wisconsin. At the Forest Products Lab, they make CNCs, the crystals, and UMaine started to produce CNFs, the fiber or fibrils. So when I came here, we already had the capacity here, right? So there is a difference in the scale, of course, when you talk about nanomaterials, because in my previous life, whenever I wanted to use anything, I had to make them myself because you couldn't really have them available readily. And also, if you had them, they were very small quantities, right? A few grams, maybe in a small vial or something. But I came here to Maine, and it was a different story because we already had a pilot plant that would be able to produce about a ton a day. So that was a big difference in the scale. So that basically was my motivation to change the way that I was thinking about using these nanostructured materials, right? Because if you have something small, and expensive, your mindset goes, okay, I might be using this as a little additive to add to something to see what happens, right? And that's what the expectation is of nanomaterials. You can use a small amount and see big effects. But for me, I soon realized that it's not going to take off in Maine because these materials are coming from wood. And wood is traditionally, these fibers are traditionally the product of pulp and paper industry. And pulp and paper industry was going down at that time. And people were all really desperately looking for a way to use the same product, but in a different way, in a value-added way. So I was thinking, what can I do to use this material, but not in small quantities, to use them in a high volume application so that the forest products industry would benefit. So that was the whole story behind the line of research that I started here.
So before I let you get into your research, I just want to make sure I've got this. Maine got the half of the project where we grind it up and not chemically process it, but we grind it up. I like how you said we liberate it. When did people figure out that nanocellulose and cellulose could be used in this way, whether in really small amounts like in your previous research or in these a ton a day, which, as an aside, is the largest production facility in the world of nanocellulose in this way, if I have that right. Like, we haven't gotten to the point where someone's producing more than that a day.
Well, there are commercial variations of these materials. I mean, the process is commercialized, so people can go and buy the equipment that they can install and produce on larger scale. But I would say the largest pilot scale production line in the world, I believe, is here. And it is now more than 1 ton a day. It is about 3 to 4 tons because we recently upgraded that into a continuous process.
So the other question is, when did people figure it out?
Well, nanocellulose in this sense is not new. I mean, this is like in the 80s when the first people discovered that you can actually grind or wash away the other parts and get to the residuals that look like a nanostructured material. But the process hasn't been really scaled before the UMaine process was patented a couple of years before I arrived. So that made it possible because the way, again, as I said, you put pulp and water in and you get nanocellulose and water out, right? So the only thing that you have here is pulp and water and energy that you add. So grinding those things in small fractions is really energy intensive. So the UMaine process made it possible to produce these materials at a lower energy need. And that is important when you want to commercialize things like that.
Okay, thank you for that. So your work is on a much larger scale than what was being done in your lab back in Tehran.
So the start of the research project that I have now at UMaine was back in 2014. So about 1 year into I was here. There was this funding opportunity from P3 Nano, which is from the U.S. Endowment for Forestry and Communities. Because for the first time in the U.S., there was some funding specifically designed for nanocellulose research. And at that time, there were 9 proposals funded, 2 of them from UMaine. And the idea there was that we had seen in the lab before that, well, nanocellulose looks like a good binder. You mix it with other things and then let them dry. They bond to each other well. But we hadn't really done research into what products you can make out of this, how you can use it, how you can take advantage of these binder properties. So I wrote a grant and the funding agency got back to me and said, well, this is a nice idea, but how on earth are you going to remove all this water from nanocellulose? Because nanocellulose is produced in water. It's like 97% water and 3% solids when you buy a bucket, let's say, right? And that 3% solid is very thick. It looks like yogurt, like Greek yogurt. So the question was, how are you going to efficiently remove that water so that you can make a process scalable enough so you can produce it on large scale? Because if you want to evaporate that water, it's a lot of energy. And I honestly didn't know the answer. So I go to the lab and I mix some of my wood particles and my cellulose. And then I started this conversation with my desire to become a magician. And magic actually happened. So, if you take some nanocellulose in your hand and try to squeeze the water out of it, you really can't do that. The material just flows from between your fingers. You can't extract the water because it has a lot of surface area So it can hydrogen bond with water molecules, and it likes water very much. So it doesn't let water go. But when you mix this material with wood particles, just sawdust, for example, and do the same thing, just magic happens. And you see that clear water is flowing from in between your fingers.
Was that an accident that you figured that out, or were you just trying everything?
No, I was just kind of at serendipity in the lab, I would say. But this observation was, I thought, wow, what you can really remove water from this stuff without needing to use heat energy, right? So you can mechanically drain water now. So I said, what is it that is happening? So I didn't know the answer, but I went back to the funding agency and I emailed back and I said, I know how to do this. And then it was successful. I got the funding and I started doing that research. So this process, now we have a name for it. It's called contact dewatering, which means when nanocellulose particles are in contact with another surface that has a lot of surface area, like wood particles or something like that, and the surface is also porous and likes water, then all this bound water that is interacting molecularly with cellulose particles will change into what we call free water and gets absorbed to that media, to wood particles or other media. And then you can compress it and get the water out. So again, we don't do anything special. It just magic happens there and it does it itself. But just finding a way to do this efficiently was the key to the success, I would say. So the first project that we started was, we thought if this is a good binder for wood particles, why not making particle board panels similar to particle board that is made with like 10 to 12% urea formaldehyde resin, which is a formaldehyde-based resin. Why don't we just completely get rid of the resin and instead replace it with nanocellulose? You're basically using wood to bind wood together. So we started that process. We made the small panels first, maybe 1 inch by 1 inch first, and then we made 6 inches by 6 inches. And we had a collaboration with the Forest Products Lab. We made 1 foot by 1 foot. And then we did 3 feet by 3 feet at the Composite Center. And then we also challenged ourselves to make actually a panel that was 4 feet by 8 feet. Right? So it's the same size that you can buy at Home Depot or Lowe's. So that was successful. The properties of the panels were quite good. They were similar or better in many properties compared to regular particle board panels. But there was one issue. This was a wet process. Particle board manufacturing is not wet. It's a dry process. So it is difficult to go to the industry and say, hey, you're using this very good, but we have this process you want to use. But they would say, how much do I pay? Should I pay to change everything, and make it into a wet process? That doesn't really fly. So then we were looking at what can we do to go find other processes or products that can actually use a wet process instead of dry process. And we identified a couple. One is drywall. So regular sheetrock or drywall materials, gypsum board. So those are made out of gypsum that is sandwiched between 2 layers of paper. And then it actually goes into an oven and cures and dries. So that's the process is very similar to our process. So we did that one successfully and recently got a grant to scale that up and work on the fire resistance also. And then the other product that we were thinking was making fiberboards, like fiberboards that are used for insulation. Then we got into that research area. That was also scaled up. We actually ran a successful trial last April. Remember that I told you we made a 4 foot by 8 foot particle board here in the lab? This took us about 6 hours to making one panel. In April last year, we ran a trial. We produced 2 tons of nanocellulose here at UMaine, shipped it to Virginia to our partner facility. And we worked for 6 hours on their actual line. And we produced 5,300 of those 4 by 8 panels in 6 hours. So that's how the scale is different this time. So these are the applications that I think are very like in high tiers, in terms of commercialization, they're close there. But nanocellulose doesn't stop there. It's not only a good binder, it also is a very good barrier. I call it my second B. So I'm in my pursuit of science, I'm looking for my third B now because I have the first B, which is binder. Second B is barrier. And I'm looking for the third B. I don't have it yet.
Do you have any idea what it could be?
I have some funny ideas. I think that B is actually a P, not a B, if you turn it around, because the other application is actually packaging. But packaging is actually using the both binder and barrier together. So, for example, one other thing that before we get to the third B, the second B is barrier. And barrier can be for oxygen barrier. A film of nanocellulose is really good oxygen barrier. And you can think about that application like food packaging, for example. You don't want oxygen to get into your chip bag. It also is a very good grease barrier. So oil and grease, let's say you're talking about paper plate, right, which is made of wood fiber, but it's not really grease resistant. And how manufacturers around the world used to make them grease resistant was to add PFAS to them. Right? So you have something sustainable, which is good, is wood fiber, but then you add something really terrible, PFAS to that to make it usable. If you're having a pizza at a party, and a paper plate, you don't want the oil to go through the plate and get into your clothing, right? So the fact is that nanocellulose is a very good barrier for oil, but it is known for many years. But what we are doing now at UMaine is we are designing processes that can actually apply that layer of nanocellulose on the surface of a plate, let's say, to make it grease-proof.
So does that involve thinking about spraying it on, incorporating it when it's made? When you say developing a process, are you starting with how, for example, a paper plate is made now and how you would wiggle your way in there so that you don't have to change much?
Yes. So our process has like 3 different types that we are working on that. We just filed an IP on that. So I'm not sure how much I can talk about it right now. But the process that we are thinking are kind of drop-in solutions because we don't want to add anything special, just maybe a small step before or after or during. But that will enable us to put a layer of nanocellulose on the surface of molded fiber and make it grease-proof. So you don't need to have PFAS added. So packaging, again, has my third B or P would be packaging. And I would say that's a kind of a combination of binder and barrier properties. Because in a sense, we took that idea of the drywall, right? So we had wood particles and nanocellulose bonding each other. And then with a paper laminate on the surface, we just reduce the surface thickness into a sheet to make it like a plate. And instead of having the layer of paper, we added a layer of nanocellulose on the surface. So we made it like a composite system, which was similar to molded fiber, but it wasn't made out of fiber. It was made out of wood particles, sawdust, really cheap. And we added that layer on the surface to make it grease-proof. And that's another line that we are working heavily now in my lab, in other labs at UMaine.
Let's just imagine for a minute, I like to live in the world where everything works out right and all my dreams come true. Let's say all of these hit it and you're able to figure out how to commercially scale it and you've got all these partners who want to take it in. Is there a limitation right now to the amount of nanocellulose that's out there to actually do this application? And if so, how would that be resolved? And I realize this may be beyond what your expertise is, but I'm just curious.
Yeah, it's beyond my expertise because I don't do that scaling to the commercial scale myself, but I am aware of the situation. It's, I would say, like maybe a catch-22 situation or a chicken and egg thing. In order for anything to take off, you need to have a good application. And in order to have that good application, you need a supply chain of the raw materials. So something should happen in the middle. I was actually giving a keynote talk the other day in Madison last week, and I showed from innovation to the market. I showed a graph of like someone was jumping over the valley of death. But then the valley of death, normally we do not have a good idea of how wide the valley is, right? So you try to jump over it, but you actually fall through. And then I joked that my lab is actually there in the valley, right? So a lot of ideas die, but some of them are successful. But the fact is that in order to have this take off, there should be someone or some people who are brave enough to risk it and say, I want to do this. I think personally, if I had the money myself, I would invest, but I'm not there. But I think it is doable. The scaling process is already commercialized, so you can produce any quantities of the raw material of nanocellulose. You can produce those. And for many of these applications, you really do not need a lot of that. because, the percentages of that is not really that high. And the layers, let's say coating layers, are very thin. So that is doable. But again, there needs to be something happening in that middle so that happens. So there are a lot of companies that are interested in that. It's not one or two, it's like hundreds. And it's not only within the industry sections that we are familiar with. There are other industry sections that are also equally interested.
Do you see this as a natural evolution of what had been, certainly in Maine, paper industry and the pulp industry, that they have so much institutional knowledge in how to transform wood? It's not just in Maine, it's everywhere. But like you said, if someone is brave enough to realize it's the same idea, it's just a different application. I like the idea of leaping over the valley of death, and I'm sorry that your lab is right in the middle of it right now.
No, I enjoy it. Climate is good. But yeah, I think it is doable, and it is not really unrealistic to imagine that these things can happen soon. But again, we are perhaps in nanocellulose research, we are where plastics were like 60 years ago. So it takes some time, patience, but it will happen.
So do you have a project or an application that you're really curious about, that you can talk about, that you would like to see if nanocellulose could make a difference with?
Yeah, one of the packaging applications that I am focused on is styrofoam replacement packaging type. So basically making foams that can be used for insulation and also protecting things for shipping. And, with like online shipping and everything, you see that there's a lot of styrofoam material used. The point is that the way that we are using nanocellulose as binder, let's say you are using like 10% of nanocellulose as binder in the structure of that foam, the other 90% is also from forest products. So it's, let's say, wood fiber, wood particles, waste from forests, residues, and those things. So I see the role of nanocellulose here as more like an enabling technology that allows us to use types of forest products residues that cannot be used normally. For example, you can't use sawdust to make molded fiber. But with the addition of nanocellulose, you can do that. That's an enabling technology here. And what I am very much interested these days is we have a kind of a foaming process. We have developed a couple and borrowed some other ones that were existing, that we can actually dry a mixture of wood particles and wood fibers and nanocellulose and some additives and dry them and then keep the volume the same. So we make a foam. You can make foams using, like, say, freeze drying, for example, but that is very energy intensive. So we don't do that. We just use a normal oven drying, for example, or microwave drying, which are efficient. And we can make foamed structures that can have good insulation properties and good mechanical properties to protect things. I think that area is also a very good one. And I think we are confident how we can make shapes, like regular shapes, like a circle or cylinder or like a prism type shape. But for complicated shapes, like a molded object or something, that's what we are working now on. And I personally feel that that would be a very good area that can be easily scaled.
So I'm going to go back a little bit to the origin or figuring out this nanocellulose. Does it matter what kind of wood that you're using, like soft versus hard?
Yeah, it matters a little bit, but not much. To that level that you are thinking about it, cellulose is almost the same, no matter from what type of wood you get it. But the pre-processing that leads to the pulping process is different to get nanocellulose, to get the pulp initially and use it to make nanocellulose.
So it's less of an issue for what you're looking at and just applying it to folks who are already doing it, whether it's soft or hardwood.
Yeah, depending on, most of these things are geographically determined. If you live in Maine, you have forests, so you get your nanocellulose from forests. You live in Malaysia, you have date palm trees, so you get your nanocellulose from those. So that's whatever you have.
And you were saying the packaging, 10 or 12% it would be nanocellulose and the rest of it is wood. Would that then be able to be composted or burned or recycled? Like, it's one of those things that strikes me very much it becomes circular, right?
Yes, both ways I think are possible. We have done recyclability assessment of our paper plates replacements. These are wood particles with nanocellulose and then a nanocellulose coating on them. We actually saw that, interestingly, the properties we put them back in water and then you can disintegrate them and make them again, right? But interestingly, we found that the properties were getting better and better after recycling, which was interesting. But we realized the reason because we were using a higher quality CNF on the surface as a coating. And whenever we did the recycling, we were actually adding a little bit high quality CNF to the mix. But that shows that you can actually, we did that up to 5 times or 6 times. I can't remember exactly. And the properties were as good as before or even better.
There's your magic that you were talking about.
Yeah, a lot of magic happens around where I am. And for the compostability, we haven't done, let's say, independent study on our material, but some other people have done that. And we are confident that there is no difference between cellulose, nanocellulose, and wood particles in this application than regular wood. Whatever happens to wood in nature happens to this. We have now evidence that certain fungus can actually eat out cellulose. So it's easy to consider that it's not a problem to leave them anywhere, like in the forest. The natural fungus or mushroom that grow there can actually digest those.
Which is just transformative when you think about, especially if you were able to replace PFAS with all the nanocellulose, like just remove that drastic impact that we've had on the environment, kind of unknowingly for a long time. Well, Mehdi, this has been a great conversation. And really, I find your work fascinating. And I'm really psyched to hear that you think scaling up on a large scale just requires a little bravery, because there's always someone who takes that mantle and runs with it, I think, or takes that baton. So I cannot wait to see kind of the next steps on this. Thank you.
Oh, that was great. Thank you very much for the opportunity.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by following us on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. And the Discover Maine theme was composed and performed by Nick Parker.